Welcome to the first of a few videos here on Assignment 5 from SPSS from the Yaki text. We'll be taking a look at simple and multiple regression. This particular episode will be on the background on simple regression. So as was mentioned in class, correlation and simple regression are very similar type analyses, and so I just want to kind of compare them side by side and use a graphical representation of each. So on the left here you can see what typically we would use to express the relationship between two variables in a correlation. You can see a scatter plot. In this particular example, we have test A on the x-axis and test B on the y-axis, and what's being graphed is each individual participant's score on each test. So each point on the graph represents a person, and their scores as a percentage of items correct on each one of the tests are plotted on each axis. Then on the right we have basically the same data set, but now we have performed a simple regression, and we are looking now at a line that represents the best fit for the two sets of variables across all the participants. As well, you can also notice that there's an equation that was populated. This actually was generated in Excel. So there's a way to show this formula or this equation that represents the line that's graphed there, as well as the r squared value of 0.4582. So that's also produced as well. So we'll talk about all of those components in this. So just taking a look back at the correlation, basically your research question is there a relationship between scores on test A and test B? So correlation is concerned with whether or not there's a relationship between two variables. On the other hand, the purpose of simple regression, you recall, has to do with prediction. So the research question for regression would be, do scores on test A predict scores on test B? So can you use scores on one test to predict the scores on the other? That seems like a pretty useful type thing to have the answer to. Under the correlation, one of the statistics that we're mostly concerned with is the Pearson R, and that indicates the degree and direction of the relationship. So it tells you how strong the relationship is between the two variables, as well as whether it's a positive relationship or a negative relationship. So positive relationship would be as the scores on test A increase, then also the scores on test B increase. Or you could have a negative relationship, so that as one variable increases, the other variable actually decreases. So that has to do with the direction of the relationship. On the other hand, with simple regression, we are mainly concerned with a statistic called the regression coefficient, and as we'll see, that is a representative of the slope of the line of best fit that's provided here in the graph at the top. The null and alternative hypotheses for correlation is that the correlation, and here this is the Greek letter rho, which is the population version of the Pearson R. So the null hypothesis is that basically there's no relationship, so that the Pearson R in the population would be equal to 0, whereas if there's evidence to reject the null hypothesis, we would say that the correlation between the two is not equal to 0, and therefore it's a significant relationship between the two variables. When we move over to the regression side, we can see now, instead of being concerned with the Pearson R, this actually is asking the question, is the slope of the line equal to 0? So there's a beta coefficient that can be used to express the slope of the line, and the null hypothesis says that beta is equal to 0. The alternative hypothesis is that beta is not equal to 0. And then finally, the effect size in correlation, the square of the Pearson R is the reported effect size, and that expresses the proportion of variance in one variable that's explained by the other. So if you knew the r-squared value for this particular set of data, and in fact we do know what it is, it's 0.4582, that tells you that about 46% of the variance in test B is explained by the variance in test A. So that's also a useful bit of knowledge there to report when you're presenting the results of correlation. And in fact, for regression, the exact same value is used as the effect size. So again, that represents the proportion of variance in one variable that's explained by the other. So whether you're reporting the results of correlation or simple regression, you would report an effect size. Now, just a note, in Yaki, he uses the capital R for the effect size for simple regression. Technically, that's a multiple R, and we would only use a capital R to represent the effect size, a capital R squared, to represent the effect size if we were doing a multiple regression. So for simple regression, you can use the lowercase r to represent that relationship between the two variables. So the two examples that we saw on the previous slide were both cases where we would be likely to reject the null hypothesis, but I thought it would be interesting to take a look at what does the data set look like if you cannot justify rejecting the null hypothesis. So here we see same set of data, but test A, test B. However, in this case, you can see quite clearly that there doesn't seem to be any sort of discernible pattern amongst the data, and that if you go from 0 to 100 as scores on test A, you can't really see a relationship between the scores on test B. They don't tend to go up or go down. And so this is an example of a case where R would actually be very close to 0 because there's no relationship between the two variables. And looking at the same data set through the eyes of simple regression, you can see here that that line is nearly horizontal, and if you recall from your knowledge of Algebra 1, a line that is horizontal has 0 slope, and so again that null hypothesis is basically saying, is the slope of that line equal to 0? And in this case it very closely is related to 0, very close to 0, and in that equation at the top there where it says y equals negative 0.0335, that actually is the slope of the line, slightly negative because it's sloping down to the right, and it's very close to 0. So that gives you a little better perspective hopefully on what those two null hypotheses are actually expressing. Next, let's take a higher level view of simple regression and just get some additional background on it. First of all, the objective of simple regression is to predict scores on a dependent variable using scores from an independent variable. So that's really, it's all about prediction. The data requirements for simple regression is that you have a dependent variable, or sometimes called the criterion variable, or the outcome variable. You'll also see that. That is a continuous variable by definition. The independent variable, or the predictor variable, is usually continuous. However, it could actually be a dichotomous variable, such as gender, or whether students are participating in a program, whether they're receiving special education services or not, whether they're considered to be ELL or not. So you could actually have a dichotomous predictor variable. In that case, the analysis would be exactly like an independent samples t-test. So you can actually use regression to do simpler analyses such as the t-test, and so anyway, that's how that works. All right, and then finally we've got three main assumptions for simple regression. The first one is that there's independence of observations. We seem to always have that one, that the individual participants don't really influence each other in any way, or they're not related to each other in any way, but they each set of data points represent independent individuals. Then there's the second assumption about the normality of the data, and thus far we've mainly been concerning ourselves with only one continuous variable. So we talked about whether those data were normally distributed across all of our groups. Here we're looking at what's called bivariate normality. Basically both variables have to be normally distributed, and minor violations of this are usually not too problematic, but nonetheless that's one of the assumptions. And then finally here's this idea of homoscedasticity, and that's a fun word to say, but there are basically looking at the variance of your dependent variable across all possible levels of your independent variables. So basically if you divide up your independent variable, you want to make sure that the variances on the dependent variable side are fairly consistent. So let's take a look graphically how you might understand homoscedasticity a little bit better. Next, let's take a look at what's meant by homoscedasticity and use a graphical representation to help you sort of see and visualize what's going on there. Homoscedasticity is the property of data where the variances for the dependent variable are similar along all levels of the independent variable. So as you go across the range of values for scores on test A, we would expect the variance of clusters of data points for scores on test B to be about the same, going from a 0 to 100 on test A. Now the opposite of homoscedasticity is heteroscedasticity, and so that means different, and the skedas part of that has to do with the variance or spread outness of the data. So let's look graphically at what we're talking about. So in the first chunk of the regression line here, this purple arrow shows about how spread out the data is along the y-axis, and going along you can see these first 3 or 4 here, they're all about relatively the same amount of spread outness. Yeah, I realize there's that one wacky point way up there at the top, but for the most part they're fairly similar or spread out about the same amount. However, when we get to scores on test A between 80 and 100, you can see they're a lot more spread out. And so this might suggest that we may not have homoscedastically distributed data, and so that may potentially be a problem. So one of the easiest ways to sort of know if your data may be in violation of this assumption of homoscedasticity is to look at it in terms of what's the overall shape of that spread of data from left to right. And in this case you can see there's definitely a funnel shape to it, or some sort of cone that makes up the shape of the spread of data. And so this might suggest that we have a little bit of a problem, but as Yaki talks about in the text, this violation of homoscedasticity, unless it's really egregious, probably is not going to affect your results from your regression and not bias your results too much. But it is something important to consider, and if you're doing regression for your treatise, you'll want to make sure that you talk a little bit about that and show a data plot, and then help the reader to understand that you've at least looked at it and considered that in your analysis. As we'll see in the next portion of these presentations, it's fairly easy to run a simple regression, and so you'll get some data out of there. I want to spend a little bit of time talking about how you actually do what you intended to do with simple regression, and that is to predict score on one test from scores on another. So how do you actually go about that? So here we are back to our same picture of performance on 2 tests, and an important component to this is that line of best fit, and we can express that line as a relationship between x and y, where we've got the terminology here y hat, which is the predicted value of y, not the actual value, but the predicted value of y, which would be right along the line, is equal to a, which is the y-intercept, the point where that line would cross the y-axis. Okay, so when it crosses 0, that's what the intercept is. And then the slope of the line is rise over run. You might recall that from your ninth grade algebra class. So that's the number of units that the line increases per units that it moves to the right. So that's the slope of the line. Here we can see a positive slope. If the line was sloping down, that would be a negative slope to it. So if I know the slope of that line and the y-intercept, then I can piece together a predictive model. So here's the equation as it looks: y equals a plus bx. Then I can actually take the values. So you'll notice superimposed on this chart in the upper left hand corner, we actually have this equation. It's written kind of backwards. However, the number that's standing by itself, that 13.1, that's our intercept, and the 0.619 or 0.62 approximately times x, that's going to be the slope of the line. And so what we can do is use that equation to actually calculate what we would expect the score on test B to be if we knew the score on test A. And so we can actually calculate that out. So here's the question: suppose we have a person who scores 60% on test A. What score would we expect that same person to have on test B based upon this model that we've created here? So taking a look at our chart, what we're basically doing is finding the score on test A, following up until that crosses the line, noting that point, and then following back over to the left, and that indicates what we would expect the y value to be. And so again, this is based upon that best fit line. So here's our equation with the appropriate intercept and slope inserted into the equation. Then we're going to take 60, which is our x value, and plug it into that equation for x, and then go ahead and crunch the numbers, and we should come up with 50.3. So based upon this model that we've created, I would expect somebody scoring a 60 on test A would score about a 50.3 on test B, with some error, because you can see that the data are kind of scattered around the line, so there's going to be a bit of error. So we're interested in that as well, and that's going to tell us something about how good of a model we've created and how good the fit is. So that's basically the conceptual side to simple regression. So what we'll do in the next session is take a look at how to actually run the analysis in SPSS. Finally, let's clear up a little terminology. We've been talking about a regression coefficient as B, but we also talked about a beta, and in your output in SPSS you're going to see both of those, so it's important you know which of the two that you're going to be interested in various parts of the analysis interpretation. So let's start with the regular B. We said that is actually what's called the unstandardized regression coefficient. Nothing's really been done to it. Recall that's the slope of the regression line when you plot the data in its original metrics. And it also tells you the amount of change in your y variable for a 1 unit change in your x variable. So again, that's basically the definition of a slope, but it's good to know that as you increase one variable, how much the other variable would be predicted to increase might be something interesting to report in your write-up. Now, on the other hand, beta is also considered to be a regression coefficient, but it's standardized. So what SPSS does is it actually takes and evaluates the regression based upon, rather than the original data, it reevaluates it based on standardized data. So it turns all the data points into z-scores, and then it runs the analysis on that. And so the outcome, instead of being in the original metrics of the study, are actually in terms of the number of standard deviations of change in your y variable for a 1 standard deviation change in x on average. So instead of being expressed in the units of measurement, it's in units of standard deviations. So looking at the bottom line, when we go to do the analysis, we're going to use the beta coefficient to run our statistical test. Remember our null hypothesis that was that beta was equal to 0, and so when we run that test to see if we have a significant regression, that's what we'll be using. On the other hand, the B is actually more interpretable because it's in the same metrics as the variables, so it's easier to talk about. If we have a 1 unit increase in the score on test A, we would have a 0.6 unit increase in the score on test B. So that gives you a little bit of background on the difference between the unstandardized regression coefficient B versus the standardized regression coefficient beta, and how we'll be using that. So we'll use that information as we run through the analysis in SPSS.